Hey XFIS class, welcome to the notes for Monday. Today we're going to dive into the pathophysiology of atherosclerosis and then look at how exercise changes that pathophysiology. And I'm going to use a video that I made last semester for the class when it went online in the spring because it's just too good not to use. And so hope you enjoy it and make sure you watch this and know it well before you come to class on Wednesday for the synchronous day. All right, so we're going to dive into a little bit of physiology here, and really it's pathophysiology, looking at the progression of atherosclerosis. Okay, and so when you're thinking about your concept maps, you have the option to choose atherosclerosis or glucose control. Okay, and in each of those, you have to outline the pathophysiology, and then show how exercise changes that pathophysiology. So what I'm about to run through here is a very detailed description of the pathophys of atherosclerosis, and this is something you would want to have in your concept map if you chose that one. Okay, so it all starts with endothelial dysfunction. So remember, we have this small endothelial cell layer that lines all of our blood vessels. One of the jobs of that tissue is to produce nitric oxide. Okay, and we can see that that tissue is not functioning well when we have decreased nitric oxide. Okay, so all of this, the very first step in the progression of atherosclerosis is a decrease in the production of nitric oxide. And the thing that makes nitric oxide is an enzyme called eNOS, endothelial nitric oxide synthase. Okay, so in endothelial dysfunction, we see decreased eNOS levels, which leads to decreased nitric oxide levels, which one thing that does leads to inability to properly vasodilate, because nitric oxide is a vasodilator, so we can't open up blood vessels as well. Okay, another thing that does is dysfunctional eNOS, instead of producing nitric oxide, produces free radicals. Okay, free radicals bind to lots of things and cause damage, but one of the things they bind to is LDL that's built up in our blood vessels, and then they do something to that LDL called oxidize it, okay, which would be pull an electron off of it, okay, and that by pulling an electron off of it, that oxidizes it, and that makes it look like a foreign invader in our cells, and that or in our tissues, and that causes our immune system to attack it, especially our macrophages. So that's an important chain of events there. Okay, and then the third thing that we see with decreased nitric oxide in step 2 here is that normally nitric oxide inhibits the expression of these little molecules called cellular adhesion molecules, and there's 2 of them here, VCAM and ICAM. There's another one in the image you'll see in a second called E-selectin. Okay, all of these, think of these as little flags that cells send out on the surface of the cell into the blood to call in the immune system. They say this is a kind of like a flag saying we need help down here, we got a problem. Okay, and so when there's plenty of nitric oxide being produced, that nitric oxide inhibits these little molecules from coming out. But when there's not as much nitric oxide coming out, we don't inhibit that. So less inhibition of these cellular adhesion molecules. So what that leads to is that stimulates platelets, macrophages, and T cells to all aggregate around that tissue, as well as migrate into the tissue to start the inflammatory process. Okay, so this leads to immune cells aggregating inside of our blood vessel walls. Okay, those immune cells release pro-inflammatory cytokines. Okay, and then so we see increased pro-inflammatory cytokines. We also see decreased anti-inflammatory cytokines. That leads to systemic inflammation and chemotaxis, which just means all those leukocytes or white blood cells coming to that area. So a bunch of white blood cells coming to that area, they're all getting called in to help. Okay, so we see that. We also see immune cells releasing things called growth factors. Again, this is a normal part of the healing process. When you have damage in an area, we want those immune cells to come in, clean it up, release growth factors, stimulate the cells to lay down scar tissue and heal the tissue. But instead of that happening in a nice way, we get laying down of collagen, but that also stimulates smooth muscle cells to migrate up from the middle layer of the vessel into the intima layer closer to the blood. And so we start getting this accumulation of scar tissue and smooth muscle cells. We'll see that on the next slide, or next two slides. Secondly, those macrophages that are called in by those cellular adhesion molecules, when they interact with LDL, especially oxidized LDL, they love that stuff. They're gonna eat it up, and they eat so much of that oxidized LDL they actually get engorged and become what's called a foam cell. And then they do so much of that eventually destroys them. And then they're just stuck there, this big fatty dead cell. So now we have part of our plaque being formed, which is made up of dead macrophages, collagen tissue, as well as those smooth muscle cells. And then we have this hard, necrotic, fibrous plaque with a bunch of fat in the center, which was that LDL. And that's really the formation of the plaque. Now that we've got the plaque, that plaque progresses to get to a big enough size to where it can actually start cutting off blood flow to that area, which can lead to more cell death, which leads to more necrotic tissue, and eventually rupture of that endothelial wall. And that's when things get dangerous. Okay, and there's a few factors that lead to a higher chance of that endothelium rupturing. Number one is something called MMPs. Think of these as like little Pac-Man. Little Pac-Man comes in, eats up some of the collagen, smooths out the tissue. This is all, again, a normal part of the healing process where we're supposed to be able to clean up that collagen, smooth it out. But in this case, it's cleaning up the collagen and breaking down the plaque in such a way that it makes it more unstable, higher chance of rupturing. Secondly, when a plaque starts to get its own blood supply, that's what angiogenesis is. Gets its own blood supply. Okay, so blood vessels start coming in, feeding that plaque. That leads to a high, not change, but chance of rupture. Again, this is mediated by a chemical or molecule called integrin. We'll see that on the next slide as well. It's another form of an adhesion molecule. Okay, so if these two things are happening, then we're more likely to rupture. So when that rupture does happen, what that does is that exposes some of that collagen and other stuff that's inside the blood vessel wall to the blood. That immediately stimulates the blood clotting process. And the blood clot is made up of fibrin, okay, and so fibrin and platelets all form this big blood clot, okay, and that narrows the artery even more, and then eventually that clot can bust loose, and then it can start rolling down the blood vessel. If the blood vessel is small enough for it to just get stuck right there, then it's going to block off the blood flow right there, and no more blood's going to get down. If it's not small enough, then it's going to keep rolling down until it finds itself in a small enough blood vessel that it gets stuck in. If that happens to be in the brain, that causes a stroke. If that happens to be in the heart, that causes a heart attack, and this is the cause of most heart attacks and strokes. Okay, so that's the progression. This slide here is a very nice depiction of that progression of atherosclerosis. So this is the healthy right here. Okay, that's the healthy vessel, and then we're working ourselves this way. This is looking at endothelial dysfunction. Okay, the first step. All right, so we see decreased nitric oxide production. We see a buildup of LDL. Okay, this LDL is also going to be getting oxidized. Because of that decreased nitric oxide, that's going to lead us right over here to step 2, which is going to lead to an increase in these adhesion molecules. Right? Increasing these adhesion molecules, that's going to bring in the immune system. Right? So that leads us right here to bringing in monocytes. Monocytes eventually turn into macrophages. Once they come into the blood vessel wall, they turn into macrophages. That's what these are. Those macrophages start engulfing this oxidized LDL. T cells also come in. When they engulf enough of that oxidized LDL, They die and turn into a foam cell. This big cell is just full of fat. We're going to see growth factors being released here too. Right, those growth factors are causing the neighboring cells to release collagen. Right, as well as those growth factors are stimulating smooth muscle cells to migrate from down here where they're supposed to be in the media layer. They migrate all the way up here to where they have no business being at all, and they become part of this plaque. Okay, so now we see this next step, we see some dead cells. That's some of those macrophages are dead. We also see the induction of those MMPs. Look, told you they look like little Pac-Man. So they're chewing up all this collagen, but that collagen is becoming less stable, and the plaque's becoming less stable because of that. So then we move over to this step. That's really where we start seeing this smooth muscle cell aggregation and all this collagen aggregation. And you can see these big foam cells now here. Moving over into this next step, we see integrin, which is a little molecule that causes the formation of new blood vessels. Okay, those new blood vessels are going to be what's leading to, so the MMPs and the integrin are what's leading to a more likely chance of rupture. Okay, so eventually this plaque ruptures. That's what's shown right there. That exposes things like tissue factor and collagen to the blood, which automatically stimulates the blood clotting cascade, which results in fibrin, which is what clots are made up of, also makes platelets aggregate, turns it into a thrombus. Okay, that thrombus can bust loose and go rolling down the artery, cause an MI or a stroke. Okay, so that's the basic flow of this. The amazing thing about this is we are going to see how exercise changes every single one of these factors as we move forward. Okay, so let's do it. All right, so how does exercise improve endothelial function? First of all, I should probably answer the question of what causes endothelial dysfunction, because we didn't really say that. We just said it happens. All right, but dysfunction would be caused by smoking, okay, sedentary lifestyle, okay, dietary factors, high blood pressure, high LDL. Wait, it's all those risk factors for cardiovascular disease, right? So all of those risk factors for CVD are what cause endothelial dysfunction. Okay, so how does exercise change this? Exercise leads to something called increased shear stress. Okay, increased shear stress is instead of blood, if we've got a blood vessel here, blood is kind of just normally just flowing through. Okay, but then when we start exercising, the blood pressure increases, so that churns blood up. Blood starts churning, kind of spinning around in here, and it's pushing out on the walls, right? Pushing out on the walls. That pushing out on the walls is called shear stress. And what we see with that is that shear stress leads to first of all, that stimulates mechanoreceptors on those endothelial cells, and that activates them. And those mechanoreceptors eventually lead to activated eNOS, which leads to increased nitric oxide release. Okay, that's kind of the acute effect, right? Acute effect. But then the chronic effects would be increased production of eNOS, which also means increased nitric oxide availability. And then if we've got increased nitric oxide, then we've got decreased adhesion molecules. All right, we've got increased vasodilation, which that's going to lead to a decrease in blood pressure. Okay, this is going to lead to a whole chain of events, which pretty much decreases the progression of plaque buildup. Okay, so there's some information and a lot of studies out there on what type of exercise might be the best for improving endothelial function. A lot of research looks at HIIT versus continuous exercise. kind of the same question of does intensity matter and why. So the idea might be that higher intensity, increased intensity, then increased shear stress. All right, so if we've got more shear stress, then maybe a greater effect. Seems to be that way with some studies, but we're not sure. Let me walk you through one study which was done on this, which was my dissertation project at ASU. And so what we did, we were the first study to really look at this in obese individuals who were sedentary. So we had 18 of them finish the study. They did 3 sessions a week for 8 weeks of either HIIT or continuous. Okay, the HIIT looked like 1 minute on, 1 minute off, 10 times. That 1 minute on, they got to 90 to 95% of their maximum heart rate. This was done on the bike, on a stationary bike. Total exercise time was a little over 11 hours. Continuous group did 30 minutes at 70 to 75. Total exercise time was 16 hours. All right, so quite a bit shorter in the HIIT group. Okay, and the main outcome that we tested in that study was something called flow-mediated dilation. Flow-mediated dilation is a non-invasive way to measure endothelial function. We have an ultrasound machine in the lab that we can do this test on as well. So the way that the test works is you get an ultrasound machine and you hold it right here on their brachial artery. Okay, and then you go ahead and put a blood pressure cuff around their forearm distal to that brachial artery. And the first step is to measure baseline artery diameter. So you get that blood pressure cuff, or you get that ultrasound machine, get a nice visual of the brachial artery. We have some software that's going to measure that. We measure that for a couple minutes, get a baseline, so get a resting level, okay, which is right here. The resting diameter would be like this, right? And then we pump that blood pressure cuff up. So we occlude the blood flow for a full 5 minutes. Okay. After that 5 minutes, we release the cuff. The body tries to overreact and send a bunch of blood down that artery, which creates a bunch of shear stress. All right. So a bunch of shear stress. And then that shear stress causes maximal release of nitric oxide, maximal vasodilation. And we wait about 3 minutes after, still measuring the artery, and we want to see the peak artery diameter, so dilation diameter, and we just compared this, the resting diameter to the dilation diameter, and the FMD number, flow meter dilation number, is that just percentage increase. So 7% looks like about normal, and the wild part about this measurement is for every 1% decrease under 7%, we see about a 13% increase in CVD events, which equals strokes or heart attacks. So a very predictive measurement. Okay, this is kind of a schematic of what that test looks like. So this would be where the blood is, inside the artery. Okay, it's flowing this way. Once we pump that cuff up, release the cuff, it creates shear stress, right? So we got blood churning around in here. That activates these little mechanoreceptors. Mechanoreceptors stimulate this whole chain of events, which leads to the activation of eNOS. eNOS produces nitric oxide. Nitric oxide doesn't go to the blood. Nope, it goes down here to the smooth muscle and causes smooth muscle to relax and causes vasodilation. Okay, this is a little image. That's not going to work for us. I have 2 videos here that aren't going to work playing on my iPad here, but that's okay. I think you'll get the idea. This is our ultrasound image of a brachial artery. Okay, this is the actual artery itself here, right? And we have the special software that measures the distance between 2 points thousands of times and gives us our average distance between all of those points to give us diameter. Okay, so it's a brachial artery. Also has a little Doppler probe right here, and that Doppler probe is going to tell us velocity of the blood flow. So every time this pumps up, we see the blood's going at about 40 centimeters per second. There's also always a little bit of backflow with each beat of the heart. Okay, and then this is the actual measurement part of it down here. This is the diameter. 0.22 centimeters or 2.2 millimeters. This is actual flow, and this is one's flow in mils per minute. The other one is another way to express flow. So when we do this test, we'll see resting diameter here, and then if I was able to play the video, you would see these kind of coming up like this, would pretty much do this, and then it would come back down. Blood flow would shoot way up when we release the cuff, and then it would come back down. Okay, and what we would do is we measure this diameter versus this diameter. We measure that distance between the two, and that's our percent FMD. And so we can see that on the next slide exactly what happened. Here's that baseline measurement. Here's the peak measurement. So the baseline was 2.19 millimeters. Peak was 2.28 millimeters. And that FMD peak was about 4%. This was an obese person who was sedentary at the beginning of my study, so they had a severely impaired endothelial dysfunction to begin. So that was the primary outcome of my dissertation study, and here's what we found. So FMD improved from 4.5% in the HIT group at baseline to 8.2 after 8 weeks. We can see that nice clean increase here. What we saw in the continuous group is it almost looks like it goes down, but this is a non-significant decrease. So the continuous group didn't really improve flow mediated dilation at all. And we published this in 2016 in the Journal of Applied Physiology. Okay, the other interesting finding here was that resting artery diameter, the one that we measured before we pumped the cup up, we saw in the continuous group that actually increased, and that was a significant increase. In the HIT group, this did not change. So what we see with this is continuous led to what we call a structural adaptation, which means the artery gets bigger, okay, whereas HIT led to a functional adaptation, which means it can vasodilate better. And that's what we saw, and that was our conclusion. So interesting stuff for sure. There we go. Okay, so we also, we've seen quite a few other studies now looking at HIT in other kind of at-risk populations or even disease populations. The one that came out in 2007 that just kind of shocked everyone was this one by a Norwegian group from main author of Wisloff, Ulrich Wisloff. He had 27 patients who had a heart attack post-infarction, and then now they all had heart failure. He made them do 12 weeks of 3 days a week of HIT or continuous. And the HIT here was actually the 4x4 protocol. So meaning 4 minutes on, 3 minutes off, 4 times. Usually considered harder than the 10 by 1. And what they saw was HIT doubled endothelial function, increased their VO2 max by 46%, increased ejection fraction by 35%, and decreased pro-brain natriuretic peptide by 40%, which is a marker of heart failure. And this is the graph of their FMD. Everybody increased, very strong. Another colleague of mine, Sid Angadi, who's a professor at ASU, I was in the PhD program with him. He did his dissertation study was a 4-week HIT intervention versus standard cardiac rehab in heart failure patients as well. His main outcome, just in 4 weeks, which was really only 12 sessions of HIT, they have a 3-point heart failure criteria scale, or heart failure severity scale would be the better way to say it. And what they saw in the HIT group is that it dropped 1 full point in the heart failure scale. That was a significant drop. There was no change in the moderate group in just those 3 3 weeks, or 4 weeks. Okay, so let's talk about all those different risk factors and factors related to cardiovascular disease that were related to endothelial dysfunction and exercise. So high blood pressure is one of those. The thing about high blood pressure is there's an acute effect and a chronic effect. So one acute bout of exercise can decrease your blood pressure by 13 millimeters of mercury for up to 8 hours. So that's huge. So if you exercise every day, then you got low blood pressure for most of the time. But let's say you can only do a 10-minute walk. That's okay. There's been studies that have looked at one 30-minute bout of exercise in the afternoon or morning, compare that to 3 10-minute bouts of exercise, and because of this acute effect of exercise, that that fractionized exercise broken up into chunks is actually better for decreasing your blood pressure. Okay, that's the acute effect. Chronic effect, we expect to see about something like this, about 6 to 7 millimeter decrease in both systolic and diastolic. And a lot of the stuff looks at, well, how hard do you actually have to exercise? Is intensity a factor? Is HIIT better than continuous? And no, it doesn't seem to be actually moderate intensity exercise, which would be like a brisk walk, is probably actually the best for hypertension. And volume seems to be the number one factor instead of intensity. So that's blood pressure. And so obviously if we decrease blood pressure, if we decrease BP, then we improve endothelial function. And that's going to start us at the very beginning. So that should definitely be part of your concept map. What about dyslipidemia? This is blood cholesterol levels, right? So physical inactivity has shown to decrease HDL levels by about 4%. HDL is the good one, the one we want to be high, right? Exercise will change your total cholesterol and your LDL levels, both bad ones. We can see those decrease by about 10 to 15%. Exercise can increase HDL levels by quite a bit, 10 to 17%. Exercise can decrease triglycerides by 10 to 20%. All of these are related to atherosclerosis and buildup of plaque in the arteries. Okay, what about exercise on inflammation? Okay, so we've got aerobic exercise. There's some evidence that aerobic exercise, a lot of evidence, will decrease most of what's called pro-inflammatory cytokines. These are all little chemicals that activate the immune system. Okay, so interleukin-1 beta, interleukin-6, C-reactive protein, tumor necrosis factor, interferon gamma, all these different ones are activators of the immune system. Exercise decreases these. Okay, and it also increases the anti-inflammatory ones. Interleukin-4, interleukin-10, and adiponectin. These are all increased with exercise. So this article right here by Balducci is a fantastic article that shows this. When you read the review article that I was a part of writing at the end of the semester, we review this one exactly. But exercise has a full anti-inflammatory effect. Okay. What about exercise on blood clotting and plaque stability? Aerobic exercise has been shown to decrease mediators that lead to plaque rupture and instability. We were just talking about those. What were they? Right there are those MMPs. It was the integrin. Also angiotensin 2 wasn't mentioned before, but that's one of the angiogenic factors as well. Exercise decreases these, which makes the plaque more stable. Okay, so more stable, which would mean decreased risk of rupture, which means decreased risk of clot, which means decreased risk of MI or stroke. Okay, and then we also see that some factors in the blood change with exercise too, so the factors that lead to clot formation. So we get decreased levels of fibrinogen, decreased levels of PAI1. That one is kind of a tricky one to understand. It's called plasminogen activator inhibitor. Okay, so plasminogen activator inhibitor. So it's a double negative because it inhibits an activator, and we're talking about decreasing. So we're decreasing the inhibition of an activator. Just believe me when I say that when we have decreased levels of PAI1, that leads to less clotting. All right, so that decreases our risk of a clot happening. Okay, so all those things are caused by exercise. Okay, so now what you can do on your own, what I'd like you to do, is I'd like you to go back to that color figure that showed the effects of, or the progression of atherosclerosis, take all the stuff we just talked about and plug in how exercise changes all of those effects of every step in the progression of atherosclerosis. And I'm going to challenge you to find where exercise changes every single one of those factors. And that's exactly what you want to do with your concept map.